Our project 1 is entitled An Analysis of T-Line Dispersion, Distortion, and the Heaviside Condition. The goal of this project is to explore the frequency dependence of signal propagation on real-world transmission lines. We will simulate 3 different signals on 3 transmission lines using Desmos to demonstrate dispersion and distortion. We will then use the Heaviside condition to eliminate it. We assume that all transmission lines used can be fabricated, and that capacitance or inductance can be added to achieve the Heaviside condition. The 3 transmission lines that we will use are the RG58U coaxial cable discussed in class, a 2-wire line, and a parallel plate line. We calculated all of the lumped element parameters for the 3 transmission lines using their dimensions and electric properties of the materials they are composed of. The 3 signals that will be used are a 100 Hz sine wave, a 1 kHz sine wave, and a 2 kHz square wave.
To see the effects of frequency and T-line parameters, it's helpful to draw them on the complex plane. The sliders on the left control omega, r', g', l', and c', and plotted on the complex plane to the right are the complex numbers r' plus j omega l' and g' plus j omega c', which I've labeled A and B for convenience. These numbers appear in the characteristic impedance Z0 and the propagation constant gamma, as shown in the formulas at the top of the screen. To keep everything at the same scale and facilitate an intuitive grasp of relationships, these parameter values are not at all realistic. If they were, not everything would fit clearly on one screen. If I drag these points around, they change r', g', l', and c'. Notice that because all 4 parameters must be non-negative, both points are restricted to the first quadrant of the complex plane. If we turn on Z0, we can see that changing as well. Because it's so short, I've extended it with a dashed line. Since Z0 is the square root of r' plus j omega l' over g' plus j omega c', its angle is half the difference between the angles of A and B, and we can see that this is true by putting B on the real axis. Because of the restrictions on the parameters, the angle of Z0 is restricted to between -45 and 45 degrees. The magnitude of Z0 is the square root of the ratio of magnitudes of A and B, which is why it's so short. If I make B approach 0, Z0 goes to infinity. Now let's take a look at the propagation constant gamma. By this formula, its angle should be half the sum of angles of A and B, which is right in the middle of A and B's angles. Its magnitude is the geometric mean of A and B's magnitudes, so gamma will usually be somewhere between A and B. Therefore, increasing omega, r', g', l', or c' all increase the magnitude of gamma. If we project gamma onto the real and imaginary axes, we get alpha and j beta, the attenuation and phase constants. The restrictions on A and B ensure that neither is negative. Now, what are the ways distortion can arise on a transmission line? It occurs when propagation depends on frequency, so that if we take the Fourier series or transform of a signal, its different frequency components propagate differently. Specifically, it happens when propagation velocity, which is omega over beta, attenuation, or characteristic impedance depend on frequency. Look what happens now when I change omega. All 3 factors in distortion also change. But when the Heaviside condition is achieved, they all stay the same. Also note that Z0 is now a purely real number. Why does all this work? You've seen the equations in class and we'll show them again shortly, but it's because r' over l' equals g' over c' means that A and B are now collinear. They have the same angle in the complex plane. This means that the angle of Z0, which is half the difference of angles between A and B, is now 0, making it a real number. It also means that the lengths of A and B are now proportional, so their ratio, which determines the magnitude of Z0, is constant. The effects on alpha and beta are less easy to see, but essentially, with A and B collinear, the projection of gamma onto the real axis, which is alpha, is constant, and the projection onto the imaginary axis, which is beta, is proportional to omega, meaning omega over beta, the propagation velocity, is also constant. Now that we've examined the relationships between parameters, let's see what some signals look like on a real T-line. Here is a 100 Hz sine wave traveling on an RG58U coaxial cable, like the ones in the lab. Here is a 1 kHz wave on the same line. Notice that it travels faster than the 100 Hz one, as shown by the vertical lines. We've assumed lossless so far, so let's turn on attenuation. You can now see from the envelopes that the higher frequency wave attenuates much faster. This is what the 1 kHz wave should look like if it had the same velocity and attenuation. The envelopes and vertical lines are now the same. These effects are distortion in action. Each wave by itself would be transmitted intact to the other end of the line, but a signal composed of the sum of the two would not. This is what the sum should look like without attenuation and with attenuation, and this is what it actually looks like. The higher frequency oscillations die out much more quickly than they should. This is especially obvious if we measure the voltage at a hypothetical load placed at the vertical line. The green load voltage line has much smaller high-frequency oscillations than the ideal orange line. The same can be seen for this 2 kHz square wave approximated by the first 6 non-zero terms of its Fourier series. Let's assume there's no attenuation for the moment. Here's what we should see, and here's what we actually see. Notice how the general high to low pattern of the pulses remains the same, but the higher frequency oscillations on top of them distort their shape. This is also visible with attenuation turned on. This distortion of square pulses is a major problem in digital circuits and communication systems. It limited the transmission speed of the first transatlantic telegraph cable to 1 letter every 2 minutes.
So we have now seen the effects of dispersion and distortion on transmission lines. Now let's see how we can eliminate it. Simply put, the Heaviside condition states that in order to achieve distortionless propagation on transmission lines, the ratio of the conductance to capacitance must be equal to the ratio of resistance to inductance per unit length. Now let's see why this works by looking at its effects on the propagation values. When we plug into this ratio into these equations, we see that we get a propagation velocity and a characteristic impedance that no longer depends on the frequency of the signal. R prime plus j omega L prime and G prime plus j omega C prime are in phase with each other, so dispersion is eliminated. To achieve the Heaviside condition, we can't change R prime or G prime because these are inherent properties of the conductor and the dielectric materials. Instead, we add capacitance or inductance in series on the transmission line. Now in doing this, we will increase attenuation of the signal, but we can fix this through the usage of amplifiers. So let's look at the Heaviside condition for each of the 3 transmission lines. In each of these cases, the first ratio is much smaller than the second. So we determine the amount of inductance we need to add to balance these ratios. We do the same thing for the 2-wire line. It should be noted that for each of these transmission lines, we must add inductance to achieve the Heaviside condition. However, this may not always be the case. Different transmission line parameters and signals may require the addition of capacitance instead. We repeat the same procedure for the 3rd time with the parallel plate line. Once again, we add inductance to achieve the Heaviside condition.
With the Heaviside condition implemented, the square waves look like this on the 3 transmission lines. They all have the same frequency, but their wavelengths and phase velocities are different because of T-line parameters. Because of the huge amount of inductance we added, alpha is much smaller and beta much larger than before. This is why the wavelengths are only a few meters now rather than tens of kilometers. So now that we've eliminated distortion, everyone's happy. But there's one thing these visualizations haven't taken into account: the skin effect. The skin effect makes R prime increase as the square root of frequency, so that if we make R prime over L prime equal G prime over C prime at one frequency, it won't hold at any other frequency. The Heaviside condition is negated. For these animations, I've taken R prime to be constant, but once the skin effect is considered, it becomes much harder or even impossible to make lines distortionless, but that is beyond the scope of this project. So, in these videos, we visualize the relationships between the T-line parameters and wave propagation, and saw what distortion looks like on a real line. We then introduced the Heaviside condition for eliminating distortion and saw the effects. In conclusion, the Heaviside condition does reduce distortion, but the skin effect sabotages this at higher frequencies, a problem that needs to be solved another way.